Hello, how are you? Uh, it's time to leave behind stacks and queues and circular linked list and start talking about a new data structure. The new data structure is a structure called a tree. Now, this is going to be a topic that will be on for quite a while because there are many different types of trees. But a tree is a very simple structure. First, we define a node. A node has one or more value field, well, I should say zero or more value fields and one or more pointer fields. So an example, let me just get those ordered. Here's an example. Struct node star brace. Let's say int val node star LC node star RC. This node has 2 pointers and 1 value. We'll use this in a while in talking about a binary tree. So we got a set of nodes. That's the first thing. Now, there are certain rules. One of the nodes is the beginning of the tree. And has no pointers pointing to it. Now, if a node points to another node, then it is the parent of that other node, and the other nodes are children. The other node is a child. So what we're saying is that this particular node has no parents. This special node has no parents. We call it the root of the tree. Now, every other node has one and only one parent. Totally non-biological. Sorry about that. Nodes with no children are called leaf nodes. They're at the bottom of the tree. Now I've got some examples of this on a handout that you will be getting soon. These notes will be going out probably as soon as this goes out. Here's an example of a tree. I can't spell mouse, but you'll notice that mouse is the root. It has no parents, and it has pointers to dog and puma, and dog has pointers to chicken, lion, and puma has pointers to otter and I put an empty there to say that there's no left right child of Puma. I could have just left it off, but I just wanted to emphasize that this is a tree that where nodes have two children. It's called a binary tree. Now here's a second example, a little bit harder to see, but in this example, each node has two values in it, separated by a comma. So I've got LT, CF, MO, UW. And then if you would look carefully, you would see that there are three children from each node. And in the leaves, I have bat, which is less than C. I have dog, which is between C and F. And I have hyena, which is greater than F. So C and F divide the three children. It's as if everything to the off the first one is less than C, or less than or equal to. Everything in the middle is between C and F, and everything in the rightmost child is greater than or equal to F. Then if you'll notice, everything in that area from the CF node down is less than or equal to L. This is actually a trinary tree. It splits everything into three parts. Now that's just two examples. There are many, many trees. We're going to see a lot of them, believe me. Let's see, where was I? I was here. The root is said to be at level 0. Children of the root are at level 1. Children of level N nodes are at level N plus 1. The height of the tree is how many levels there are, the levels. So I've got that written out here also for you. You'll see, that's not the one I wanted, sorry. This was the one. And that's not the one. It's the middle one. Now, I think I wrote that out somewhere. Here we are. The height of a tree is the maximum level of the nodes in the tree. So in that case, this is level 2. We have 0, 1, and 2. And this is also level 2. Height 2, pardon me. Next, this is the one. Now, why do we use trees? Well, that's to make searching easier. You probably talked in 103 or 104 about some searching algorithms. And if you search just an unordered list, it's going to take, it's not a very good search. You're going to have to search a lot of things. If you search an ordered list where things are from lowest value to highest value, alphabetically say, then if you just go one by one by one by one until you get to what you want, or you're beyond what you want, it's going to take you on average about halfway through the list before you know if what you're looking for is in the list or not. It would be like taking a telephone book and starting at the first page. If you wanted to look up Murphy, you'd start at the first page and keep going until you get to the Murphys, and that'd be a long time. Now, a better way to search this is called a binary search. In that particular way, you jump into the middle and decide which side you're going to be on for what you're looking for. And you keep doing that and doing that and doing that. Well, if you look at my first example tree here, you'll notice I organize this tree as a binary search tree. If I am looking for a chicken, I will go to mouse. It's not mouse, but it's less than mouse, so I'll go to the left child. It's not dog, but it's less than dog. I'll go to the left child, and there it is, chicken. And I've only looked at 3 nodes, not all the nodes. If I were looking for a hyena, I will look at mouse. It's not mouse, but it should be to the left of mouse. I look at dog. It's not dog. It should be to the right of dog. It's not lion, but hyena, effigy, HIJKL, so it should be to the left of lion, but there's no node to the left of lion, so it's not in the tree. Now, actually, this tree is the same kind of thing, but this one breaks it into 3 pieces at each level. If I'm looking for dog, I notice in the first node, dog should be less than L. So it goes to the leftmost of the pointers. In that node, I notice that dog should be between C and F. So I look in the middle of the 3, and there it is, dog. Again, if I were looking for ape, I would go, well, ape is less than L, go to the left. Well, ape is less than C, go to the left. Well, ape should be less than bat, but there's nothing there, so ape is not in the tree. So the idea here is that this is a faster way to search. It cuts out a lot of things. There's another reason why trees are interesting. Let me go back to here. Every node of a tree is the beginning of a tree. The node and all its children, its, I guess, descendants, is a tree. You can see that over here on the example. If you ignore mouse and just start at dog, dog is the root, and chicken and lion are the 2 children of dog. By the same token, puma is the root, and ma'ata and empty are the children. But it goes a little further. Chicken itself is a subtree. It doesn't have any children, but it's the root. Why is that important? Because it allows us to use recursion, which is a powerful way of writing a lot of programs we're going to look at. This allows the use of recursion. In fact, the very first program we're going to do has recursion in it. So that's the idea, that we're going to be creating trees. Now we have to have a way to read in a tree, set up a tree. And what I've done is I've created a program, which you will get. And it's a program that I'm just using to look at binary search trees. I have a node, and it's traditional that the children are called left child and right child. And I happen to make it a val and an integer just to have something simple to play with. Then I wrote a class, myTree. I put the my in front of it because there may be a built-in class called tree, and I don't want to bump into it. And the private part's very simple. It's just the root, which points to a tree. And I initialize it as null. The tree is empty. Now public, you get to declare a tree, as usual, myTree. And then I have read a tree. And read a tree is a very short program because it sets up a set of recursive program. Read a node reads one node and then its children. And it does it recursively. We'll look at that in a few minutes. Write a tree is the same way. It's very simple. It starts off a recursive writing. And there is the write a node. Add a node does the same thing. It goes to an auxiliary function. Often that's the name given to the one part of this pair of functions. So now let's look at how I'm going to manage this. Before I do that, I want to go back here, and I want to go to this one, and I'm going to show you a file that I created. This file here, you'll be getting that. You'll notice it looks like nothing. But the way to read it is that the first line is the root of a tree. The value in that root is 29, and the yes in front of it means it has a left child, and the yes after it means it has a right child. The next thing, I start off by reading that root. Read that row. I create a tree with one node in it. Then I see if the left child is yes. If it is, I read the next node. That's the left child. I connect it up. I check to see if it has a left child. If it does, I read the next node. That's the left child of 18. Now I look at 12. It does not have a left child. Does it have a right child? Yes. So I go and read the right child of 12. Now I get to 15. It has no left child and no right child. I've already done the children of 12. I've already done the children of 18. So now I'm up to the y, the second y in 29. And that will take me to the 61 and so on and so on. So this is set up for a recursive read. Again, this is the root, the right child, and then as long as they're y's, I keep going down. The minute I don't get a y, I go to the right. I start down there. When I finish a node, I pop back up, and wherever I was, I finish that, I pop back up, and so on until I get back to the root. That's the way to read. Now, in my program, here's how I did that. The main program is very simple. It creates a tree, and it sets up that file, opens the file. Now I'm going to read a tree. All I'm passing in is the file handle. So let's look at what read a tree does. Read a tree says, read a tree up here. Read a tree says, I want to call read a node with the root. A root is the pointer to the beginning of the tree. We started off root as no. So now I get into the read a node. Read a node, this first part is all an awful technical thing to pull apart the line of input. I have to get the value of the left, I have to get the left value, the right value, and the value in the middle that I'm going to be putting in, the storage value. So I basically have to play around with it to get everything there. Now, if the root equals null, I create I have root point to a new node I create. The new node is just, I'm just calling it X to have something to call it to. Remember, X was what I passed in, and I can change it. So if it's the root, I let X, I let the root be the same place as X. So it's pointing to the same item. Now I look at, again, another technical thing. I have to put in the value string to I. What string to I does is it takes the value of a string, and if it looks like a number, it converts it to a number. If it looks like an integer, it converts it to an integer. It's a nice, fast way to make something into an integer. All right, the value's in. If the left part of the input was a Y, then all I'm going to do is repeat this whole thing to read in the left subtree. Else, the left subtree is null. Now, if after I do that, I've read the whole left subtree, now I look at the right. If the right is Y, I read the right subtree. Otherwise, I set it to null. Now, there's the recursion. This part here sets up the node I'm working on. This part here sets up the left subtree. If there's no left subtree, the left child of X points to null. Otherwise, X point to left child is X. And that's where I'm going to read in. I'm going to have that point to the root of the left subtree. And then I do exactly the same for the right subtree. Now that pattern is going to appear over and over and over again. Basically, I may do something at the main at the node, go left, then go right. Or I may go left and do something at the node and then go right. It's over and over and over. So once I get the whole tree in, which I do pretty fast, I'm going to write the tree. And again, write a tree is a recursive routine. It's what is called an infix writing of the tree. So let me write that down on what I'm doing over here. When we have a binary tree, one way to write or search the tree is infix method. In writing a tree, this means that we write the left subtree, the value in the node, and then the right subtree. Now let's see how many mistakes I made. Now this one has to be changed. Now why would it be called in? It's called in because the tree itself, the value itself, is in between the two children. We often search in the same way. Well, we might not do a search that way. We might use what I'm going to use next. Another method of writing is the postfix method. Here we write the left subtree, the right subtree, and then the value in the node. It's post because the value in the node comes after the other two. Now you might guess there's one third one. The third method is prefix, which means right value in node, right left subtree, right subtree. And these are, all three of these basically are the same program, just moving a few things around within it. I have just written for you a infix writing of the node. Look how simple it is. If x left child equals null, write the node on that side. If then write the value, then go to the right, write the node down that way. And write a node produces the whole subtree. I probably should have called it write a subtree, but I thought it was reasonable this way. It's like 3 pieces, very simple. It just says, go left, write what you have in the node, go right. And again, I had to make it so that the first part was different from the others. So that's why I've got write a tree, and then that goes into write a node. So the last little piece to look at in this program is adding a value. And again, it's the same idea. I pass in the value I want to add. Then I have to call the routine to add it with the root. Again, I'm allowing that to change. Now I have a node T2, and what I'm doing is saying, well, if I have that value already, see out the value is already in there, else if the x value of the child is greater than, if the value in the node is greater than what I want to put in, then I should go left. Because v is less than what I want to put in, so it should be on the left side. Now, if there's no left side, then it's not there. It's just not on that side. And that's the else here. Oh, pardon me. First they say we go in, we look, and we keep going down. We recurse. So we go to the left. If it's the root of that left subtree, great. If not, keep going. We go right, if it's greater than, and that basically is it. That's how we manage it. Now, I think I wrote this in such a way that it will always add. Yes, it'll always add. I didn't worry about getting down to the roots, to the leaves. So does this program work? Let's take a look. I've already run it once, but I'll run it again, closing this window. So let's see. I set it up so it read in, it showed me what it had read in. And then I wrote it out in order. You can see these numbers are in order. Then I added a 5, I added a 100, and I added a 20. So this is after the additions. Now, a point that most of you haven't been worried about much, unfortunately. When you test a program, you should test the possibilities that you might get. You'll notice I tested putting in a number that will be at the beginning of the result, putting in a number that will be at the end of the result, and putting in something in between. Those are the 3 possible cases. So I need to test all 3 of them. Now, all of this material I've been writing, I'm going to send to you in a short time. You will get this that I have been writing as we have gone along. You'll also get the notes. There'll be notes 9. They'll go out there. And you can get tree values from here, but I'll probably send you tree values as a second file. You're going to do a homework on this. One of the simpler homeworks you have to do, believe it or not. You're going to take my program, which writes things out in infix, and you're going to write it out in postfix. Now, that's not hard. It actually really doesn't involve any new writing. It just involves some rearrangement of things. So I'll try to get that to you at the same time. So good luck now. Oh, and by the way, if you haven't started on homework 7, you better. Homework 7 is not easy. It's not that it's hard coding. It's that you have to understand the problem. And I've had several students work with me. They're beginning to understand the problem. In some cases, they've got it done, I think. But you need time. If you wait till the night it's due, I don't know if you're going to get it. And the same thing is true of homework 8. You have to work at them. You have to get the algorithm before you write the program. Don't go straight for the code. Write out what you're going to do. Make sure you understand how to do it. In problem 7, there is a worked out example. Take a look at it. Make sure you understand it. Then you can start filling in the code. Now, that's my sermon for today. I'll get off my pulpit here and leave and end. So long now. I hope that I can find the place to stop this. So I guess I'm going to have to go here, here, and here, and here, and here. And I still can't find a way to stop this thing, but I think I will. I hope I will. I know what I have to do. I have to basically go here, move this, so that I can get to the stopper. I may have an infinite program. There it is. Fine.